بسم الله الرحمن الرحيم. وما أوتيتم من العلم إلا قليلا. صدق الله العظيم. برعاية السيد رئيس جامعة بغداد المحترم، وبإشراف كل من السيد عميد كلية علوم الهندسة الزراعية المحترم الأستاذ المساعد الدكتور نصير سلمان كاظم، والسيد رئيس قسم مكافحة التصحر المحترم الأستاذ الدكتور حسن علي عبد الرضا، يعقد وعلى بركة الله قسم مكافحة التصحر ندوته العلمية العالمية الافتراضية تحت عنوان التقانات الحديثة في تحسين إدارة التربة ومكافحة التصحر. يتفضل السيد عميد كلية علوم الهندسة الزراعية المحترم الأستاذ المساعد الدكتور نصير سلمان كاظم لإلقاء كلمته، فليتفضل مشكورا.
شكرا جزيلا. بسم الله الرحمن الرحيم، وبه نستعين، والصلاة والسلام على سيد المرسلين محمد وعلى آله وصحبه أجمعين. السادة الحضور الكرام، السلام عليكم ورحمة الله وبركاته. بداية أحب أن أشكر قسم التصحر متمثلا بالسيد رئيس القسم الدكتور حسن، وجميع منتسبي القسم والسادة المساهمين في هذه الندوة على دعوتهم لي للإشراف وافتتاح هذه الندوة المعنونة التقانات الحديثة لإدارة وتحسين التربة ومكافحة التصحر. كما أحب أن أتقدم بجزيل الشكر للسادة المحاضرين الدكتور إبراهيم البكري خبير وكالة الدولية للطاقة الذرية، والبروفيسور ستيفن أندرسون من جامعة ميزوري. Welcome, Doctor. We appreciate your participation in our symposium. شكرا جزيلا للجميع، وأتمنى لهذه الندوة المباركة أن تسلط الضوء على كيفية إدارة وتحسين التربة خدمة لتحقيق الأمن الغذائي والاكتفاء الذاتي. شكرا جزيلا لكم، وأتمنى لكم الموفقية والنجاح.
شكرا جزيلا دكتور. يتفضل السيد رئيس قسم مكافحة التصحر الأستاذ الدكتور حسن علي عبد الرضا المحترم لإلقاء كلمته، فليتفضل مشكورا.
شكرا جزيلا. بسم الله الرحمن الرحيم. السيد عميد كلية علوم الهندسة الزراعية المحترم، السيدات والسادة الحضور المحترمون جميعا، السلام عليكم ورحمة الله وبركاته. أرحب بكم في هذا المساء أجمل ترحيب في الندوة العلمية الدولية الافتراضية التي يقيمها قسم مكافحة التصحر في ظل هذه الظروف الصعبة والاستثنائية التي يعيشها العراق والعالم بسبب جائحة كورونا. نسأل الله لكم جميعا الصحة والسلامة. الأخوة الحضور، اسمحوا لي أن أرحب أجمل ترحيب بالضيف الكريم البروفيسور أندرسون من جامعة ميزوري في الولايات المتحدة الأمريكية لتفضله بقبول الدعوة لإلقاء محاضرته الخاصة بتحسين التربة والبيئة في هذه الندوة، متمنيا أن تكون فرصة مناسبة لنا جميعا للاستفادة مما سيتم طرحه، فله منا كل الشكر والامتنان. كما يطيب لي أن أرحب كثيرا بالبروفيسور الدكتور إبراهيم بكري المحترم مدير عام متقاعد وزارة العلوم والتكنولوجيا بقبوله الدعوة لإلقاء محاضرته عن التقانات الحديثة في مكافحة التصحر، متمنيا له دوام الصحة والتوفيق. Please allow me to welcome our guest, Professor Anderson from the University of Missouri, United States, whom I thank for accepting our invitation to give a lecture in our virtual international scientific symposium. Despite all the obstacles we are facing these days during the COVID-19 pandemic, it is also my pleasure to welcome Professor Dr. Ibrahim Bakri from the Ministry of Science and Technology, Iraq, and thank him for accepting our invitation. I extend my thanks to all the audience who have joined us in this symposium through Google Meet, hoping that everyone would engage and ask about the new technologies that will be presented in today's lectures. Thank you all.
شكرا جزيلا دكتور. سادة الحضور الكرام، أستميحكم عذرا للحفاظ على التشويش، يرجى غلق المايكات والكاميرات. يتفضل دكتور صلاح لتقديم دكتور أندرسون.
اوكي. السلام عليكم. مساء الخير للجميع. اتمنى الجميع يكونون بصحه جيده وعافيه، خاصه في هذا الظرف الاستثنائي. Good evening everyone. I hope that you are doing well and stay healthy and safe, practically in these extraordinary times. طبعا بداية جدا سعيد حقيقة لهذه الدعوة المباركة المقدمة من قسم مكافحة التصحر على المشاركة وعلى تقديم الدكتور أندرسون، مشكورا لقبوله أيضا للدعوة. I would thank. I'm really glad to meet you today to participate in this kind symposium. Hopefully that will be very nice and will be helpful to you guys. And also I would أيضا أقدم الشكر للسيد العميد الدكتور بروفيسور أسيستنت بروفيسور دكتور نصير سلمان على أيضا انضمامه إلى هذا الندوة. I would first of all I would thank Dr. Nasir for joining us. Thank you, Doctor. And also a special thank to Dr. Hassan also for kind invitation and for hosting Dr. Anderson and me in this meeting, and also for significant effort for preparing this symposium. And also special thank other to the Dr. Abdul Ghafoor for hard work. Thank you, Dr. Abdul Ghafoor. حقيقة بالبداية كذلك أحب أشكر دكتور أندرسون على قبوله هذه الدعوة الكريمة وإلقاء محاضرة إن شاء الله تكون قيمة مفيدة للجميع. I would appreciate, thank you, Dr. Anderson, for accepting this invitation, and I hope that this lecture will be helpful for all my colleagues in Iraq. So طبعا بداية قبل ما أتكلم عن أعطيكم بعض النبذة عن دكتور أندرسون. أنا تكلمت مع الدكتور أندرسون قبل المحاضرة. أنا اليوم عندي شعور مختلف. لأول مرة أنا أقدم دكتور أندرسون الميتينج فور خمس سنوات. هو البي اتش دي ادفايزر مالتي، هو قدمني عدة مرات. فاليوم أنا كل سعيد حقيقة دا أقوم بهالمهمة. Today I have really special and private and strange feeling that I'm presenting to Dr. Anderson today for several reasons. You did present me several times, so I'm really glad that I'm doing that today. بالنسبة لدكتور أندرسون، بالنسبة للسي في أو background, I will give you some background information about him. He's from America. هو من الولايات المتحدة الأمريكية. He received his bachelor in agronomy in 1980 from Brigham Young University. طبعا حصل على البachelor مالته بالهندسة الزراعية سنة 1980 جامعة Brigham University. He received his master in soil science in 1983 from North Carolina State University. الماستر سنة 1983 جامعة North Carolina. He received his PhD also in soil science in 1985 from North Carolina State University. كذلك he is Albert Distinguished Professor of Soil and Environmental Sciences in the School of Natural Resources at University of Missouri. طبعا هو بروفيسور مع مرتبة الشرف في قسم علوم التربة والبيئة في كلية الموارد الطبيعية. طبعا سكول بالمناسبة الأمريكان يحبون يقولون سكول، ما يحبون كولج، بس هي نفسها يعني سكول هي كولج يعني. جامعة University of Missouri ولاية ميزوري الأمريكية. Now he is director of the Soil Health Assessment Center in the School of Natural Resources at University of Missouri. طبعا هو اليوم حاليا هو مدير مركز تقييم soil health. I assume that you are familiar with this term soil health. This is very famous term and أعتقد جدا معروف هذا التيرم. He has been a professor in environmental soil physics and Veda zone hydrology for 35 years since 1985. So حقيقة هو يعني أستاذ بالبيئة فيزياء التربة وكذلك هيدرولوجي وحركة المياه بالأوساط البوردز ميديا بالوسط المسامي منذ سنة 1985، يعني أكثر من 35 سنة هو يدرس. He was published over 150 Harvard Journal articles and 18 book chapters. طبعا هو عنده أكثر من 150 بحث with high quality journals these journals which actually are which have very high impact factor. And also he is the fellow. He's a fellow of the Soil Science Society of America and fellow of the American Society of Agronomy. So طبعا هو زميل Soil Science Society طبعا الملتقى وكذلك الهندسة الزراعية. والعام الماضي في مدينة سان أنطونيو في تكساس طبعا كرموه لأكثر من 40 سنة هو membership هنا في هذا المنتدى. Last year he was awarded for 4 years membership in the Soil Science Society of America. He was awarded in the San Antonio, Texas, United States of America. He has advised 17 PhD students to completion. طبعا هو أشرف تقريبا على 17 طالب دكتوراه أغلبهم international. Most of them are international students. He is really support. He is really professional. How can to deal specifically with these international students because different language, different cultures. Yeah, it is really kind of them. And also he teaches courses in the environmental soil physics, transport in Vida zone, pollutant, fate and transport, watershed modeling using GIS and hydrologic and water quality modeling. طبعا هو حاليا درس 4 كلاسات فيزياء التربة وكذلك الجريان في الاوساط المسامية ونقل ومصير الملوثات وكذلك موديلنج واترشيد مستجمعات المائية باستخدام تقنية الجي اي اس وكذلك موديلنج واتر كواليتي. طبعا دروس انا يعني الحمد لله تمكنت من اخذ جميع هذه الكلاسات جدا مفيدة. Finally, his research interests focus in quantifying and assessing soil hydraulic properties and processing in the landscape as affected by soil management. طبعا مادة الشغل هو تركز على التقدير الكمي والتقييم والتقدير الكمي للصفات والعمليات العمليات طبعا الفيزيائية and landscape as affected by soil management. Today he's going to present improved soil, water and environmental under conservation buffer management. Please welcome with me Dr. Stephen Anderson. Dr. Anderson, you are very welcome. You have 25 minutes to 30 minutes to present. Thank you so much for joining us. The mic with you. Thank you.
You want to put yours on? Anyway, greetings. This is Steve Anderson. Thank you for the kind introduction. I'd like to thank the honored guests with us, leadership from the University of Baghdad, also from the college, the dean. Thank you so much for the kind invitation. And unfortunately, challenging times we were having, but obviously we're still working on very significant challenges with agriculture production and such matters. And just to share kindness, Dr. Salah, he's Dr. Salah Al-Ghil now, and he's been a very good student with us, been a great ambassador from your country here in the United States with our university, very hardworking, and has done a very good job. And so obviously I'm going to talk about things related to types of work we're doing that's similar to his, but he will probably share with that when he returns, okay? Anyway, thank you so much. Just a bit of an overview, just a kind of a perspective here. We have about, and this is in Missouri, and this is kind of related also to the north central region of the United States, places like Iowa, Kansas, Iowa, Illinois, Indiana, Ohio. This area, we're a little bit further to the west of Ohio, but we have about 1,000 millimeters of rainfall per year. Now, that's obviously a very different sort of setting than where your place, the University near Baghdad, is serving many areas of Iraq, that you probably have something in the order of 200 millimeters of rainfall per year. So very, very different challenges associated with it. And so one of the big challenges we've had, and so the focus of these studies will be what I'm familiar with here in our area, which is focusing on issues relative to soil erosion. Because we have this rainfall coming, and sometimes we're worried about now with the changing climatic settings and maybe more intensive storms, and still challenging us with soil erosion, okay? So the studies, I'm going to talk briefly about that at the beginning here, so you put it in the context of these conservation buffers, vegetative buffers, and why we're using these, okay? So I'm going to talk about a couple of selected studies In each of those, I will talk about the results from each of those studies and also share some conclusions, okay, of these studies, and then talk briefly about Dr. Salah Al-Ghil's work that he may present more detailed when he returns at your university. So the first segment here is management to reduce soil erosion. So in the Midwestern United States, several conservation practices have been used to reduce soil erosion. Just a little history. At the University of Missouri is where the beginning of the universal soil loss equation was started. Okay? So if you're working in soils, you've probably seen this. Universal soil loss equation was helping us to understand and be able to predict and use management to reduce soil erosion. Okay, so the original plots here on the campus still maintained to do this. And so one of the things that we can do with management, we can't do much about the climate where we're at. We can't do much about the soils, but we can do something about the length of the slope. And so that's used in the universal soil loss equation, some of the other conservation practices. So the broad-based terraces, which we use a lot in northern Missouri and other parts of the Midwest, these handle more gentle slopes, but some areas are a little bit steeper. And one of the studies we're going to be talking about is a vegetative system trying to contrast with the narrow-based terraces, which are on steeper slopes. And of course, these terraces need grass waterways to be able to handle the water that's diverted. So what we're trying to deal with is cut down the slope length to be able to reduce the erosive challenges with these soils, okay? And then, of course, if we keep the cover on that with conservation tillage, including no-till, we can make some benefits as well. Of course, moving into what we're going to talk about today is using vegetative buffers, and some of these with appropriate plant changes and things may be of some use to help the soil water management challenges, even the desertification, the increase in deserts. If we can reduce the migration of those, maybe using some kind of plants will help us. And that's what we used historically in the Midwestern US to help handle some of those challenges, okay? So winter cover crops, and in the area where, as Salah mentioned, soil health is a big focus in the United States.
Please, Dr. Anderson. Please, Dr. Anderson. There is no presentation. There is no presentation.
Oh, really?
Let me look. This is...
دكتور صلاح ماكو اي برزنتيشن ترى.
Sorry.
ما نسوي شيء.
Oh yes, present now. Okay. And then entire screen. Okay. And then is that okay?
Yes, click here.
Click, oh yes, click here.
Sure.
And then share. Oh yeah, thank you.
Yeah.
يعني من البداية ترى بس حكي ما نسمع شيء.
ايه.
Is this, can you see it now? Thank you for mentioning this. Sorry.
Okay. Thank you. Okay, continue.
Okay, thank you so much. So just
هسه واضحة الصورة عندك عزيزي؟
نعم، السلايد اللي يقرأ management to reduce soil erosion.
ايه اوكي كويس.
Thank you so much.
Yes. So could you start like a little bit in the beginning because they didn't see.
Okay, good. Yes. So again, just to briefly mention what we're presenting here is focusing on erosion issues, because again, the challenges we have with the amount of water, and some of these selected studies and results and conclusions from each of those. Okay. So in the Midwestern United States, one of the challenges we have is this soil erosion, at least in our area. And so we're looking at broad-based terraces. These are handling for more gentle slopes in the lower left, right over here. And then the narrow-based is these, it's steeper country. We have some of these in Iowa and northern Missouri as well. And then the grass waterways to be able to handle this, okay? And obviously what we're going to focus on talking about today, I want to put it in the context. We're using some vegetative buffers, okay? And they're helping us to handle this issue with slope length, okay? To reduce that. And so one of the issues with the soil health program in the United States, there's a lot of effort now to basically help subsidize landowners with winter cover crops. And of course, they grow something to keep the soil covered during the winter, and then also handling planting directly sometimes into the plants with those settings, okay? Again, apologize for not getting these presentations loaded. Another thing where these vegetative buffers has is these contour buffer strips. And so sometimes we grow a lot of corn and soybeans in the Midwest, and then we'll put a permanent vegetation in these contour strips. And so our conservation buffers are kind of replacing some of these contour buffer strips, okay? And so some of these vegetative conservation buffer strips that we're going to be talking about are stiff stem grass buffers, which were used in a place where we had these narrow terraces, narrow-back terraces in the steeper land. Some agroforestry buffers. The uniqueness here at the University of Missouri is we have a Center for Agroforestry, does a lot of international and national work to help use trees, and we'll describe these systems here briefly. And maybe some of these can possibly be used, again, probably different species, but some other work maybe in the Middle East. And then grass buffers, which have been used for a long time.
This دكتور صلاح.
نعم.
الدكتور ترى نفس السلايد باقي، يعني هو ثابت عليه لو.
لا هو دا يتحرك هسه. لا هو دا يتحرك.
لا ما عندنا نفس السلايد باقي. overview of presentation.
هسه دكتور تحرك لو لا طلع لك.
هسه تحرك. هسه تحرك.
Okay. Is it working? Yeah.
Thank you, Salah. Thank you again for keeping us on track. Doing these virtual meetings, we always have technical difficulties sometimes.
دكتور حسن إذا صارت أي مشكلة رسم صفر. Okay, go ahead.
All right, so we're going to talk about two vegetative buffer studies, and this is a little bit some of the areas that's related to this that Saul was working on, Saul when he was here. And so the first one is assessment of stiff stem vegetative buffers kind of used in a setting where those narrow base terraces were used. And we're going to look at the effects on hydraulic properties, infiltration, and then we won't have time to get into the watershed, but we also extended these benefits of this also to simulate the benefits that it actually had on runoff and then sediment loss, okay? And the second study was an influence on agroforestry and grass buffers on hydraulic properties and hydrology and understanding some of those benefits of these systems, okay? The first one here is looking at these vegetative buffers on this. And again, Saul, I can share this with you if you want some of these publications. Ahmed Rockman, who was a PhD student with us, helped focus on this. So the first study here that's mentioned in the Transactions American Society of ABE, which is American Agricultural and Biological Engineers now, was where we basically simulated on a watershed the benefits from these stiff scrap hedges and their hydraulic property changes and looking at runoff and sediment changes, okay, in terms of yields. Both compared that with measurements that were done on that watershed. Okay, we're going to talk a little bit about computed tomographic measurement of soil macroporosity, something I've been working on for a few decades using that tool. And then we're going to talk about the hydraulic properties and infiltration of these. Okay, so water stiff stem vegetative buffers. Now these actually are used internationally at different times when, you know, resources aren't there. A lot of times we have resources in the US, so we can bring the bulldozers and heavy equipment out and shape the land, but it's quite expensive, okay? And so that's how those terraces are set in. These stiff stem perennial grasses are planted on the contour. Now we sort of have to plant them on the contour about 2/3 or 3/4 up slope on the landscape because we're constrained in the width of these because we have mechanized planting and mechanized harvesting. So we have to keep these equidistant to be able to work, okay? So they're a little bit off the contour as we move down slope and a little bit above slope. Okay, and these help to reduce redistribute the water and reduce sediment loss, okay? And they're narrow. Typically, these are bunch grasses. One of the ones that Saul has been using, we often use switchgrass. It's a common grass, native species here. And it's a bunch grass, but we keep these in narrow areas. They can kind of be a leaky dam and basically help us reduce this runoff water, okay? And this is just a demonstration of what's going on. So if you see on this left side, here's the water coming. It comes to this, and these basically slow the velocity of the water down because we have a challenge with that, with these big storms. And then they basically leak through and they deposit the sediment upslope. So this is the deposition zone that's collecting the soil rather than getting down into the streams or the waterways. basically keep this on the land. And so we were interested in looking at this issue. And this was quite a successful successful study in being able to look at the benefits of these, okay? This soil in this area is a deep loess, okay? Deep loess, and traditionally used for corn and soybean production, but it has challenges because of the steepness. This is rain-fed. We have enough water here. We don't have to use irrigation. We can grow sufficient productivity on this. Okay, so this study, we designated 3 sampling areas. One in the grass hedge. We sampled in the soil below that, which we right here in the grass hedge. The deposition zone, as you saw, basically the soil has not developed. It's just recent deposition. And then up here in the row crop area, which is pretty traditional management associated with that, with the corn and soybean rotations, okay? I'm just going to show you some brief results from this. So again, the effect of these treatments here on the bulk density. This is in gram per cubic centimeter, same values as gram per cubic centimeter or gram per cubic meter. Here's the row crop, these boxes, solid boxes. This is very typical of what we see for this particular soil. Notice the grass hedge, okay? Grass hedge basically lowers the bulk density because we have these deep roots that go through this, at least near the surface. And of course, the deposition zone, notice it has a higher bulk density because the soil hasn't had sufficient time, even though it's recently deposited, to basically develop the petrogenesis properties and development of the structure associated with that soil. So basically by the 3rd and 4th depth here, we're not finding many differences, but up near the surface. Now this has a huge effect on the hydraulic properties, and we're using laboratory-based core samples. We also did some in-field infiltration, and this is a comparison of the saturated connectivity, okay? This is on a log scale, millimeters per hour. Again, our depths. And so notice again the row crop, the RC, which is these boxes here, very typical values that we get. Notice the grad head, highly improved in terms of hydraulic connectivity. Now, those are just those narrow strip areas that we've had in that watershed. We find almost, not quite, about 6 times increase in our hydraulic connectivity, which is so we can get more of that water in the soil and less of it running off. And that's always the way, even I know you've worked a lot on water use efficiency. It's the same situation. Can we basically use the water more efficiently and basically not lose it? And interestingly, the deposition zone, these zones right in here, the triangles, basically lower hydraulic connectivity is associated with those. I was a little bit surprised the deposition zone would not be that different, than the grass edge, but it actually is. We also did water retention, another important hydraulic property. These are understood core samples, put these in basically pressurized chambers, saturate them, and then desorb them at various pressures. And then that's for undisturbed samples, and these are showing the shorter distances we need in order to get the fluid flow to equilibrate, and you probably have some of these in your laboratories. Okay, now we'll show you in the next study more of the water retention relationships, but we use this to basically help us understand the pore size distribution, because this is really what's affecting the hydraulic properties, okay? So the pore size distribution, we've done this for many decades here, and I know Sala did some of this with his work as well, determined from water retention measurements using the capillary rise equation. We classify these pores into 4 macropores. We can see these with a naked eye, greater than 1,000 micrometer effective diameter, coarse 60 to 1,000 micrometers, 5 mesomores about 10 to 60 micrometers, and the micropores, which is about 10 micrometers. And so the field capacity, just to kind of put it in context, field capacity, they're basically controlled by these micropores, okay? So let's look at these for this particular study. So the macropores, again, very typical values we see with the macropores for the row crop. This is kind of what we typically expect. Deposition zone, decrease those, but the grass hedge really improved these macropores, which is why we have such a huge effect on the hydraulic conductivity. Of course, the coarse mesopores are also important a little bit for fluid transport. Some effects of these up near the surface, but these effects decrease with depth. And then fine mesopores, a little less effect, and micropores, no significant differences in these, okay? So all this management, these vegetative buffers really impact the bigger pores, which are important for us to get the water in the soil and having less runoff. Okay. I'm going to talk a little bit now. Another way we have of looking at these pores is using computer tomography. Okay, if you're familiar with this, this is a medical scanner. We also have some other types of scanners to get a higher resolution, but we're using this also for soils. We've been doing this for about 30-some years here at the University of Missouri. Okay, and what we do is our soil, and then this is a cutaway. We have an X-ray source, an array of detectors. These spin around the sample. You get about 1 times 10 to the 6th, about 1 million numbers per slice. And then the back projection with the computers basically help us see that structure in that sample. And then we can do this across the entire soil core length to be able to characterize this. This is just a cutaway of one of the medical scanners. And here's the sample placed here and put in the middle of this gantry. Again, normally these are used for human patients, and we're using this, expanding this a little bit for the soil. Okay, so the CT scanner generates images of the structure based on attenuation coefficients as these relate to density. And so you see this picture here. We put these, rather than in a metal ring, we put these in a plexiglass because it doesn't, the problem is the metal will attenuate or reduce the penetration of the X-ray beams. And so we use the plexiglass to hold this. But these are very similar samples we did in that first study. And you see the black areas. The black areas are air-filled pores. The gray areas here are kind of the regular soil. These white areas are iron and manganese concretions because of the atomic number associated with iron and manganese that gives us these bright spots associated with that. So these are all, with the medical, they're related to water attenuation, but we can scale these in different ways using numbers we are related to. You can use this in 2D, that's this particular image, or you can put this in 3-dimensional, which is very, very useful to look at this relative to fluid flow. Okay, so you can look at these macropore features. This medical has about a millimeter scale resolution. We have some other scanners that get down to the micrometer resolution if we're interested in that, but it's more expensive. And then we can relate these on fluid flow properties, okay? For this particular study, we had, again, using that 1,000 micrometer diameter for the macropores. Of course, the resolution of this medical doesn't do quite as good as the water retention. So these mesopores were put in the 200 to 100 micrometer diameter. These will just show you some briefly. This is one typical image. This is our grass hedge and row crop and deposition zone areas from that site. This is the grayscale. These are just boxes from the center of a core. And then what we do is we use thresholding. There's different techniques for this. Thresholding, what is an air-filled pore and what is a solid area. And so this one, the binary, are just doing white and black, just simple. We have more sophisticated and for other studies we can do, but you can see basically we have more pores with the grass hedge, fewer with the row crop, and deposition zone even less, okay? And then this, we put some numbers on this. These are CT measured macroporosity. So here we see this big differences with the grass hedge. You know, here's our typical ones down around 0.03, something like that, relative volume. These are up almost, you know, 3 or 4 times higher, okay? Now it does decay because again, the roots deposition zone is even lower. And of course, as we move through this, we can see that decrease. But it's just another way, a more detailed way of looking at the pore size. Water retention is useful, but these, with these CT, the tomography system, we can get a little bit nicer quantification of this, okay? And then we also did some water infiltration, some field measurements, okay? Just to show you this, typically we're gonna do infiltration cumulative is the way we usually do this, is millimeters and time in hours. These are done kind of in the spring of the year, 2 different years. The solid dots are basically measurements. And then the green and amp equation, as some of you are familiar with, has been used a lot. Parlange, another equation, and Kostyakov. Again, the green and amp Parlange fit a bit better for this particular unit. Let's just compare the numbers from, you know, typical treatments. This up in the upper left here, this is the grass hedge. Notice the y-axis here. This is around 800 to 1,000 millimeters.
Yes, 1 second, because the presentation is not clear here. I don't know.
Okay. You want to come
دكتور واضحة الصورة يمكم؟ دكتور؟
ماكو صورة صلاح.
ماكو صورة؟
نعم واضحة. نعم واضحة.
أستاذ نور الدين
واضحة؟
ما حد يشوفك يعني هسه قلت لك انا احسن حاجه شو اسمه؟ انا
Okay, so the upper left here, this is the grass hedge. Notice this is about 800 to 1,000 millimeters over that roughly 3-hour period. The row crop is quite a bit lower, only 50 to 100 millimeters in that 3-hour period. And the deposition zone, notice again another scale down even further, roughly about 10 millimeters over that 3-hour period. So you can see quite distinct contrasts. Let's just show the numbers. This is kind of summarizing the average infiltration rates. This is equilibrated infiltration rates over time. A couple of different parameters we use to do that: absorptivity, the early phase of the infiltration, and then kind of getting the conductivity, hydraulic conductivity from the field with these. We can see this was done, published in a paper a few years ago. So we notice we have about 6 times higher hydraulic, infiltration rates with the grass hedge and the row crop. Row crop is very typical for this soil. It's published data in the surveys. And then down about 4 times lower, about 10 millimeters per hour in the deposition zone. And now we had one other tool. We'll just do this briefly. Tension infiltrometer. If some of you may be familiar with this, it's allowing the water to infiltrate under tension. We basically restrict this, and then we put this in. We set this up and do these infiltration. This again was done with that grass hedge particular unit in one of the years. And so here we see the deposition was very, very slow. Deposition zone was very slow. So it was beyond the sensitivity of this tension infiltrometer unit to be able to make those measurements in a reasonable time. So here, when we see 0 tension, this is like our ponded infiltration numbers, okay? And so we can see this is about over 200 millimeters per hour for the grass hedge and just under 50, around 40 millimeters per hour for the row crop. And then we put it just under, this is a very small amount of tension. We put it under 50 millimeters of tension. It reduces it substantially from the grass hedge, a little bit in the row crop. By we get to about 100 millimeters of tension, almost no difference by 150. This is a very small amount of tension, but we can see the huge effect of those macropores. Once you remove those from participating in the flow, the decrease in the infiltration. Okay, so briefly conclusions. Obviously, pretty straightforward. Saturated hydraulic conductivity was very high. Water infiltration was better onto the grass edge relative to the row crop and deposition zone. Results attributed to the macropores present on the grass edges. And we looked at water retention to assess those, computer tomography to assess those, as also the tension infiltration to assess those, okay? And these results helped explain the runoff measured from the watershed. We didn't share that, but this is helping us to understand. That's what we found, and we were trying to understand, so that's why we spent time on the hydraulic properties, basically to understand, and then looking at more detail of the pores to be able to explain that system. Now, from a practical standpoint, usually these, in America, we typically use these with bulldozers. We come in and shape the land and put in those narrow terraces. But in some settings, these stiff stem grass hedges is a much cheaper way, perhaps, to be able to control the erosion on some of those. Plus, the nice thing is it's easier to change those if they, to maintain and such. And it makes it look a little nicer than doing that. Okay, let's look at the second study now, looking at agroforestry and grass, looking at some of the similar type of evaluations. We use hydraulic properties and hydrology. Okay, these are the series of references. We also did some watershed modeling in the second paper that's listed here. Okay, so what is agroforestry? This is a land use system, and again, Dr. Salah Alagil is using this for his study. You can use management system in which trees or shrubs are grown around or among the crops or pastures. And these buffers help to protect the soil. That's what we're interested in, but also gives you another economic benefit. So in these trees, if you have some kind of a nut or fruit, beneficial, or wood products, this can be very beneficial. And in case you have to be invested longer term to get these to do this, but I think it's a very nice system. And obviously some areas in the United States are starting to use these as well as internationally, okay? And these have many conservation benefits, increased biodiversity, obviously the erosion issue we're concerned about here locally, and then improved water quality, okay? Because they basically consume some of the nutrients and help us to, in that runoff water, reduce that. And then also grass buffers can be able to use. We're going to look at this. Okay, so this study was looking at, these were with grazed pasture systems. And so rotationally grazed, which is very nice. You move the cattle across all of these little areas routinely, so they consume the grass equally, cause less challenge with erosion and compaction. We have a continuously grazed area, which was causing challenges. And then also our agroforestry buffer, these were cottonwood trees, and then the grass buffer with that system. Okay, you're just showing the bulk density effects. So we're here, rotationally grazed, very common for this, but substantially reduced for the grass buffer and the agroforestry buffer in terms of the bulk density near the surface. And the continuously grazed increased because of the cattle compaction and things like that in the areas. Hydraulic connectivity, we found this, again, log scale. Some very nice numbers with the buffers. Okay, here's our rotationally grazed, and very significantly reduced near the suffer for the continuously grazed pastures. Significantly lower hydraulic connectivity. Okay, here's our water retention. You can see that effect with this. Very flat curve with the continuously grazed because it's compacted. There's rotationally grazed, and then enhanced porosity, and then water retention. Getting the water into the soil and then allowing it to basically be removed, storing that for better enhancing the plant available water with this. We also looked at pore size distributions and also found for these, even though the rotationally grazed, okay, is a perennial grass, it still has lower, slightly lower macropores compared to these buffers. And of course, the continuously grazed was substantially reduced, especially near the surface. We also looked again with computed tomography with these. These are tomography measured number of pores with depth, okay, with depth for these. Again, notice the grass buffer and the agroforestry buffer have higher numbers. Discounting the number of macropores, okay, and then relating this to CT measured macroporosity, which is significantly enhanced in these grass buffer and agroforestry buffer relative to the rotationally grazed and continuously grazed pastures. Okay. We also did some infiltration measurements on this. And these show, again, just typical replicates here. The grass buffer and agroforestry buffer higher than rotationally grazed and continuously grazed. You can see these, the y-axis here basically helps show that kind of benefit. Right. And here's some numbers. Let's just look at the field saturated hydraulic connectivity, and you can see the grass buffer had a much higher value. Agroforestry buffer not significantly higher than the rotationally grazed, but obviously numerically higher, and then the continuously grazed, the lowest value. And so significant from these studies, obviously similar hydraulic conductivity was enhanced, higher infiltration, and basically these buffers, these vegetative buffers, are in helping us to get more of that water into the soil and storing that for other time periods, okay? We had more macropores present, obviously using water retention tomography to assess those. And although pasture systems have perennial grass, compaction by cattle may affect the macropores and soil properties in watersheds under some of these management systems. So having the buffers associated with that was some benefit. All right. Just real briefly, we don't have a lot of time left. The effects of the agroforestry and grass buffers on soil water dynamics. This was in a different soil. So remember the first soil I said was a D+. The soil for the agroforestry prior to study 2 was also a D+ soil. This study, the last one, was on a clay pan soil. The subsurface has a significant amount of smectite clays. These are high shrink soil clays, really dominate the hydrology. You get a lot more runoff off those soils. And so they're putting these agroforestry buffers and grass buffers to help us manage that a bit. Okay. And I'll let Dr. Salah Aldigil, when he returns, talk more about this study. But these are some of the publications that he's done some very nice. In fact, the first one, I'll brag on him a little bit. He already got an award from the Soil Science Side America Journal on this first publication. So very interesting kind of features. So hope this is somewhat useful to you. I worried because our precipitation is so much higher than obviously in Iraq. It's different contexts because we're trying to use these systems. But again, these systems help us with the environment around the these management systems, really change the climate a bit locally, and they can really help us get more water in the soil and be more water, get better water use efficiency for some of these studies. So hope this is of some interest in your group. I know Saul is interested in maybe looking at perhaps some conservation, obviously very different kinds of plants that don't consume the kind of water these ones we were talking about, adapted for use in Iraq to be able to do that. So thank you very much for your kind attention. And as I understand, after the next presentation, we'll have time for some questions. Thank you. And I want to brag, Saul was a great ambassador for your country, a very good efforts at the University of Missouri here.
Thank you, Dr. Anderson. Thank you very much for your nice presentation. Thank you. الآن يتفضل دكتور إبراهيم بكري الكويسي بإلقاء محاضرته. دكتور إبراهيم البكري غني عن التعريف، أستاذ خبير الوكالة الدولية للطاقة الذرية، مدير عام متقاعد دائرة البحوث الزراعية وزارة العلوم والتكنولوجيا. اليوم يتكلم لنا عن حزمة تكنولوجية متقدمة لمكافحة التصحر في سهل ما بين النهرين في العراق. تفضل دكتور إبراهيم.
Thank you, Dr. Salah, and many thanks to your guest, Dr. Anderson, for the very fruitful presentation. And I hope that all of your students and the staff make use of it for their studies and future studies in Iraq. Though it's very much expensive because we cannot afford to buy such expensive instrument, but we need such kind of studies really, and this is opening very good field for us. For me, what I want to present you today is something very essential to Iraq, and we need it badly because desertification hit hard the country in terms of the soil salinization, especially in the most arable land of Iraq, which is most fertile land, which is the Mesopotamia. And now it's 80% of that land at the present are salt affected soil, and it is out of agricultural production for the time being. And it's really, it's not easy to get this land back in agriculture again, simply because conventional reclamation process cannot be done. Simply because it's very expensive in order to install drain system for the entire area. Secondly, there is no fresh water available for us to reach the salt down. So you have no choice, either to leave it, to abandon this huge area, or you find some other means to use it. If you don't use it, it means it will be the whole area of Mesopotamia will be a source of salt and dust to the neighboring city, to rivers, and to the water bound in the area. So you have to do something about it. Okay, now where's the water? The fresh water, we cut our share of the Euphrates River and Tigris River by our lovely neighbor, the Iranian and the Turkish. So you have to live by whatever left. The water left is just enough for vegetables, and essential fruits. This is why we work very hard in order to develop this package of technology to make use of this huge land. If I want to go back a little bit and present the definition of desertification for your student and for the staff, desertification has been defined as a land degradation in arid, semi-arid, and dry sub-humid region resulting from various factors, including climatic variations and human activities. So this is, we agreed upon some statistics. This is a very important one in order to pinpoint and to show you how much important this process, this natural process, which developed by the human being. Am I clear? Everything clear for you guys? Hello, hello. You hear me?
Yes, yes, yes. Go ahead. Very nice.
Yeah. Okay. Okay. So some few statistics, like according to United Nations, 30% of the Earth's land surface, which is 4 billion hectares, is threatened by desertification. The bulk of this area is in rangeland. Okay. Desertification is one of the greatest environmental challenges today and a major barrier to meeting basic human needs. Thirdly, worldwide desertification process costs $42 billion, and it's advisable to focus on prevention because attempts to rehabilitate desertified area are costly and tend to deliver limited results. Total deserted area worldwide is 46 million kilometers square. Of these total area, 13 million kilometers square, which is 28% in Arab Peninsula. Imagine this, the problem as this big. Okay. What causes of desertification is the climate and the human. And the climate, you know what, we cannot intervene with the climate, but we can change it if we want, okay? And this is long story, how you can change the climate. You can, for sure, you cannot change the macroclimate, but you can change the microclimate, okay? So the human overgrazing, which removes vegetation cover, and then over-cultivation, which exhausts the soils, and this is really happened to us because our land has been under intensive use since the Akkadian, Chaldean, Ashurian, and Babylonian. So thousands and thousands of years. So it is over-cultivated area. Deforestation, and we are very good at that one to remove the trees and left the soil bare. And poorly drained irrigation system, and this is very common in Iraq. Strategy to reduce desertification. What is the strategies? We have to develop a plan. We have to upgrade it and sustainable water management. We have to planting more trees and the roots hold the soil, as our guest mentioned in his work. The importance of the vegetation, the importance of the trees in maintaining good soil condition, and sustainable agriculture that promotes sustainability of ecosystem in Iraq. The main point of our suggested strategy, and I hope that we can work on this strategy all together, but unfortunately our work is, we work by ourselves, nobody help, nobody want to contribute. First of all, we need the desertification information system, and that information system will help us to find and localize the deserted area, the potentially deserted area, and the rate of the desertification. And we start a huge project in order to determine the rate of desertification per year. But unfortunately, we face a problem with the United Arab Emirates because the previous year map of Iraq cost a lot of money, and we need the vegetative map. And then from this vegetative map, we can calculate, you know, how much area is covered, and then how much the vegetative receding with time. But you find that it costs a lot of money, and we don't have that much money to buy all these maps in order to calculate and determine the rate of desertification in Iraq per year. Then we need to have capacity building for staff and institute. We need our staff to be very well trained. We need the institute to be upgraded in terms of instrument, as our guests show you the kind of instrument you have to use, the kind of instrument. There's all kind of instrument available in the market which help you to protect your soil, which help you to rehabilitate your soil. And then we have to work on rehabilitation of degraded ecosystem. And that one include deserted arable land in mid and southern part of the country, which is my focus for tonight. The second one, depleted soil and red feed area. And the rain-fed area, usually in the northern part of the Iraq and Nineveh, this area again depleted area because the whole area is under intensive agriculture, and there is no input from the farmer, like fertilizer, crop residue, human manures, or nothing input in the soil. So the result, you come up with depleted soil. And then there is a huge land over there in the middle of Iraq, which is the gypsiferous area, and that gypsiferous area is almost degraded land and deserted land because of its physical and chemical characteristic, and it needs special treatment in order to revive this huge land. Rangeland, it's most of the rangeland, and especially in the western desert, all of it degraded and unfortunately unfertile right now. And then most of the farmers left that area. And again, the water measurement, it's very essential to have exact measurement of water, because if you don't know how to measure the water, you cannot manage it. And unfortunately, we have been facing that problem. And then the third things in this strategy, we have to have educational program for whole population in order to respect the water and respect the natural resource and to treat them really well. Okay, now what we focus now, as I told you, we have the whole Mesopotamia salt-affected soil, and this salt-affected soil, I told you there is no fresh water for it, there is no drain for it, there is no natural drain for it. Salt-affected soil, it has to be rehabilitated in order to be converted to agricultural land again, eliminating important source of salt to nearby agricultural land and water resources, and promoting new practices for land reclamation and saline water utilization. The concept of this technology is utilization of waste abandoned land, which there is no fresh irrigation water available. That one use chemical and organic amendment for reclamation, both saline groundwater and salt-affected soil. Using phytoremediation practices, which involve cropping salt-tolerant plant, trees, shrubs, and forage crops to control salinization process, improve soil condition, and reducing salt load of the soil. And the reason, as I mentioned several times, scarcity of fresh water, high cost of conventional reclamation, no natural drain, rehabilitation deficit, and to rehabilitate displaced families, because millions of peasant family, farmer family left the area to the cities, and it costs a lot of trouble over there. And then we need the agriculture product. Now, before I get into the technology, I have to discuss with you the process of soil salinization. The process of soil salinization is not immediate one. It takes long time to accumulate the salts. And the salt accumulated over there cannot be removed by one flushing. And this is what happened in the past during the 70s when the previous government installed the drain system and they start to leach the soil and then they handed it back to the farmer saying it's reclaimed soil now. And in fact, they are not reclaimed. And I have one of my students, Nuruddin Shawki, and then we found that after the reclamation, so-called reclamation process, which have been done, we found that there is 60% of sodium left in the soil. So this 60% of the soil, with time, with less than 6-7 months, it returned back because it re-equilibrium, and then the sodium went back again to the soil profile, to the soil, and then the soil salinized again. And what is the excuse of the scientists over then? They said that the farmers, they don't take care good of their reclaimed soil, and they apply a lot of water, and this is why the soil resalinized again. And in fact, it's not the case, because according to our humble information, salinization turned the soil to monoionic form, which is sodium form soil, sodium saturated soil. Sodium saturated soil, it's not easy to remove the sodium out of it. Okay, the excess sodium, yes, you can remove it, but no, you cannot remove the whole sodium out of the soil. So you need replacing iron. And lots of people argue. They said, okay, we have calcium and the soil is calcareous soil. Well, calcium carbonate is a crystalline one in a crystalline state. So it's sparingly soluble mineral over there. Then it cannot contribute. There is a little calcium in the water itself. So we need to have calcium. Okay, if there is a calcium in the soil, so how come sodium come on the exchange side? You know, according to the allotropic series, yes, but the sodium can go to the exchange side because of the concentration of the sodium much higher than calcium. This is why we have sodium saturated soil. This is why we cannot leach the soil. We cannot reclaim the soil by just adding water. And this is what we have done. Okay? So our research finding confirmed that calcium added to irrigation water or to soil solution is markedly reducing the hazardous effect of sodium to plant and soil. We have to add calcium. I know a lot of scientists in Iraq, they don't agree with us, but you have to do it. If you want to reclaim yourself really well, if you want to reclaim your water really well, you have to add calcium from external source or internal source. How I can add calcium? Why I have to add calcium? Because don't think that just the electrical conductivity is the mental factor, because it tells me how much the osmotic potential. No, the sodium absorption ratio is very detrimental factor. If you have sodium absorption ratio, whether in water or in soil, more than 12, then forget it. There is no green cover over there. So you have to reduce the sodium absorption ratio. How do we reduce sodium absorption ratio? We can easily reduce sodium absorption ratio by adding calcium. And we have several experiment in hydroponic, in greenhouse, and in biosaline agriculture experiment, and we prove this one. Okay. As we agree that our soil contains 25% of their total constituents as CaCO3, then direct acid application or acid forming material have been used for liberating calcium from its mineral in soil. And you can use it because Iraq contains huge amount of sulfur, and we have huge product factory for producing sulfuric acid. So you can use sulfuric acid, the root solution of sulfuric acid. Okay, so you add sulfuric acid to the saline groundwater in a concentration. I'll show you very, very dilute concentration, and it's economical one because it's not expensive at all. Then the acidified water will liberate calcium and will bring this sodium absorption ratio down, and then you will improve the soil infiltration, you improve the soil hydraulic conductivity, and you maintain your soil particle, and you maintain everything is beautiful. The other source, this is what we call it indirect source of calcium. The direct source of calcium is the gypsum. We have huge amount of gypsum up in the western Iraq, close to phosphorus industry in Akashat, and you have millions of tons just waste material over there. And this one can recover the entire Mesopotamia because it's excellent source of calcium, and it has little acidity in there, which will improve the soil condition, and it will improve the reduce the sodium hazard to the plant. Okay, and these things, it's not merely talking, we have tried. Okay, and I'll show you. We choose 10 hectare piece of land, and 10 hectare, which is 40 dönüm in Iraqi measurement, and we apply this concept to it, and then we have the river water, saline water, and then water plus calcium level 1, saline water plus calcium level 2, and saline water plus 0.045 normal H2SO4. Imagine how much diluted is this one, and it's not costly. Any farmer can afford it. And the 6 treatment is 0.1 normal H2SO4, and that was fair enough to make the miracle. Okay, and this is the soil we are dealing with it. You see the soil with this 15 decimals, the soil pH pH 7.7. Although the pH, I don't believe there is any merit or any value for pH measurement in calcareous soil. Simply, we have to go and measure lime potential because pH will change easily with little bit of change of carbon dioxide. So we have to go to other one, use lime potential in calcareous soil. Sodium absorption ratio, as you see, is 21.94 in the soil, and in water is 14, which cannot be used. Okay, and then you moving on, and don't mention it that the soil texture in the Celtic clay loam, which is almost heavy texture soil. With all these conditions at hand, when we apply our treatment, the whole story is different right now. Okay, you see, we got yield over there from wheat and corn, and this is the yield we got it, and the land start to improve year after year, and we can have your student to go and visit the entire area, and the entire area now we can show you the first photos that we have for it. It's completely abandoned land, salt affected land, no vegetation whatsoever, and now you find it as if garden. That area using this kind of technology. Okay, and this is the effect of sulfuric acid on the hydraulic conductivity and on the sodium removal. You see the sodium removal, how much increase when we add 0.01 normal H2SO4, which means we irrigate with 0.01 normal H2SO4, which we have a small barrel, and that barrel dropping water and dropping H2SO4, only water in the channel or in the pipe, and that take it to the field. So it goes to the field instead of go just saline water, it goes acidified saline water, okay? And that acidified saline water make the whole difference. And as you see how much is the difference when you have the water, see the sodium, the lower curve, green one, no, the blue one is the sodium removal when you have only water, and see how much is the difference when we add sulfuric acid 0.1 normal or 0.01 normal. And again, this is the sodium removal from the other kind of soil. This is the sodium absorption ratio, my friend. And as you see, the sodium absorption ratio, when we have H2SO4, see, it's very much down and all of it below 10. And at this level, you can grow your plant easily. You can bring your farmer to the area once again with little support from the government. Okay, little support from the government for the farmers to adopt this technology. You can convert the whole Mesopotamia again, back again, and put it back again in agriculture production, in agriculture system. And when you initially for first year, okay, for the first 2 years, for sure, you have to grow salt tolerant or halophyte plant palatable to animal. And then you ask the farmer not to grow wheat or barley or corn. You just grow this kind of halophyte plant palatable to animal, and you can bring your goats, your camels, your sheep over there, and little by little the soil start to improve until you get into excellent condition to the limit that he can grow whatever kind of crop he you want. Okay, and this is for the other soil, because we have two kinds of soil, which is the Shura and Sabakh soil, and the same. There's a lot of improvement, and SAR is dropped down below the limit. Okay, and this effect of gypsum on Sesbania. Why we use Sesbania? Sesbania is a good animal feed, and it's good reclaiming crop. It improves the soil condition really like magic, because it's legume crop, add a lot of nitrogen, add a lot of organic material to the soil, improve the soil physical condition, improve everything in the soil. So we need to introduce such kind of crop as a crop rotation, and it will improve your soil condition. Okay, and then after all these trials, we want to enhance the productivity of the land. So I have one of my students, Dr. Sadiq, with me, Sadiq Jafar, and he has finished his master's degree with me on the use of organic matter, okay, in enhancing the productivity of salt-affected soil, okay, and under this technology, and then he proved that the organic material that we add it must be a factor in reclaiming such kind of soil, because it improved a lot, and I'll show you some of his results. Here is the organic matter content, and here is the soil depth. And here, when we add the organic matter to the soil, and as you see, when we have the control, then the organic matter in soil, very little. But when we add corn cob, or we add peat, or we add manure, then you have the organic material increased along the profile, soil profile, which improve the soil condition over here. And if you improve your soil condition, improve your infiltration, improve your soil aggregate, that will reduce this evaporation from the surface, reduce the salt accumulation again on the surface. So you need such kind of practices. And this is the whole objective of his thesis. And then again, another kind of soil, and the same results we obtain. And here is under fresh water and under saline groundwater, and under both cases that organic matter did the best job. And then we had our soil improved a lot by adding organic matter. And you don't need to add large quantity of organic matter. You have the crop residue, so you can incorporate your crop residue within in soil instead of burning it or collecting it and throw it away. No, don't do that. Just incorporate the crop residue with the soil and adding little urea, little nitrogen to it in order to enhance the decomposition, and you find it will work very, very good for you and improve the soil condition and improve the soil productivity. Okay, and I can follow all of this about the impact of this kind of package of technology, and how it improves the soil condition, see how the organic material, how it helps to reduce the hydraulic conductivity, because it fastens movement. You see, it speeds the movement of water, increase the hydraulic conductivity, increase the filtration. So there's no salt accumulation in the upper surface of the soil. This why the electric conductivity reduced. This why the soil start to improve day after day. Okay. In summary, addition of organic matter, the conclusion of this study, and all of it, all these studies are published in international journal. Addition of organic matter to upper 20 centimeter of salt affected soil, increased level of organic matter content along soil profile down to 60 centimeter depth. Okay, when 0.5% of corn cob peat or corn cob peat or manure added, infiltration rate increased by 60%, 38%, and 32%. As you see, that the increase in infiltration or in hydraulic conductivity depends on the type of organic waste you're gonna add. But at any rate, any kind of organic material you add, it will improve the infiltration rate, the hydraulic conductivity, and it will enrich and improve the soil aggregate, and it will improve the soil condition as well. Okay, feature of salt affected soil, I believe most of you are very much familiar with it. This is if somebody outside of Iraq see this one here, believe it's snow, especially our guest Anderson, if he is there, he will think this is the snow. No, it's not snow. It is salt accumulated on the surface. This is after removing of the salt, and this is after leveling. And in here we introduce the EM38 electromagnetic induction system in order to draw the contour map of salinity contour map. Okay, and this is available in our directorate for everybody to use. We can offer. And this is the kind of the map we get, and that will help you to understand the salt distribution in your field, and it do it very fast and undisturbed. You can draw the contour map for the entire field within 1 hour or less. Okay, and this is the type of the contour map, another type of contour map, and this is the saline groundwater, and we have submersible pump. We got it. This is when we started in our field, and this is after 1 year. You see that the cotton, like almost like a tree. This is myself and some of my staff over there. Okay, and this is the farmer, and this is rice growing over here, and the farmer and his family. We bring them back, and then we have trees, we have shrubs, and he start to grow honeybee here, and start to sell some of the honey he got out of it. Okay, this is all of the trees growing very well, and he got a lot of oil, all of them from it. So it's very productive one. This is the Sesbania, and we need to grow Sesbania. See the Sesbania how to grow on salt-affected soil, abandoned soil. Soil you cannot believe that the soil can support any kind of plant. See how this soil, and this is the cotton. The cotton tend to be tree. You see, and this is the dead palm tree over there, and all of them start to now to have fruit in there. Okay. This is the acacia, and this acacia is very important for the farmers over there because they can grow a lot of honey over there. Honey cell, they put it over honey and honeybee, and they make a good money out of it. So they are so happy with it. Okay, and this is in winter. This is the barley. That area, which is as you see it, is like snow. This is the barley. See how it improves. Just gypsum and sulfuric acid, added it in wise way and do it in a proper way on condition that the saline groundwater with a salinity up to 5 decisiemens, 5 to 6. You cannot use saline groundwater like seawater, 50 or 40. No, it has to be 5, 6, something like that, which is saline groundwater, brackish water. Okay, and you don't need fresh water. Okay, so we have to help the farmer to get to that aquifer and pump the water out of it and crop their land. Okay, and this is the barley. Honestly, this is barley exactly in the same area, and we're very happy about it. Okay, this is myself and some of the worker and one of our staff. Okay. So this is the way. Now I will go back a little bit. If I have the time, I want to introduce you and your staff to new topic. The topic is the determination of the erosion, but instead of using the very advanced technology used by Dr. Anderson, which they can afford it, we go to use radioisotope. Okay. And then for the erosion, we have water erosion, wind erosion, chemical degradation, and physical degradation. Water erosion is the most important one for us. And why we use radioisotope? Because radioisotope is fallout. And this fallout is universal, everywhere, anywhere. And there is certain radioactive isotopes which fall on the soil. It can go to 0.5 centimeter, 1 centimeter, 2 centimeter in soil, and stay there, like cesium. And it's very, very long half-life. Cesium-137, we use it to determine the rate of erosion in soil, and easily. That we have done it under the supervision and help of International Atomic Energy Agency. Okay, so you see the cesium, the source of the cesium, like the bomb in 1963 and 1954. There's a lot of cesium, and this cesium all over the world. So there is two things come out of it. Cesium-137, you can go and determine the specific activity of cesium-137 in certain remote area which has never ever been touched by human, and then go to the other area which has been under intensive or under human use. Then the difference between specific activity, you can tell you how much erosion was there. Not that one only. Now myself and Dr. Mabit yes, this we can use it everywhere, anywhere, not in Iraq only. And this one, you see, there's one issue which we cannot solve it yet. We are striving to solve it. If we can determine, if we can determine the cesium specific activity in a remote area, and we said this is the mark of Iraq, the specific activity of cesium in Iraq, such and such, while in Saudi Arabia, such and such, in Iran, such and such, in Turkey, such and such. Then when we have the storm, we can tell where does come from, because we know the mark. So the mark will tell us, but this one we cannot sure about it yet. We are working on it, but we don't finish. But in terms of determining the erosion, yes, we're doing that one, and we do it precisely. But unfortunately, recently we have been stopped because they don't let us to have any kind of instrument measure. This is the principle of the. This is the most important instrument, which is gamma detector. Okay, my friend, gamma detector. The gamma detector, it has sodium iodide detector in it, or it has germanium lithium detector. In this case, we have to use germanium lithium detector because it is highly sensitive and it's highly accurate. So whatever low the radioactivity of cesium over there, we can measure it. Okay, see this small pot. This small pot contains the soil. The soil sample, it should be 1 kilogram. Why 1 kilogram? Because to collect as much as radioactivity as we can. Because radioactivity subjected to probability, and you need to count it for 24 hours. Then you have accurate measurement. Then you have accurate measurement and calculation in order one you can tell how much erosion had happened. Okay, and I will show you some of our. Hey, this is remote area. This is Hatra Hadar, منطقة الحضر, which is nobody over there. Area which nobody there, must be nobody over there. It has never been cropped. No human being over there. Nobody touch it. So this one is, we call it the benchmark. This is the first point that we have to have, and then we bring it back and we determine the radioactivity, and they said we have the radioactivity this much. Then the entire area of northern Iraq will be measured against this one, okay? And we can determine how much, okay? How much soil have been lost, okay? Without the need of sophisticated instrument. And this is kind of the sample we get, because we have to get it down to 50 centimeter, okay? And this is another area. And we have another sample we have 3 samples for Iraq to cover whole Iraq. One in Hatran, the other one in Badra, close to the Iranian border, and the third one close to Saudi in Al-Qara, منطقة القعرة, close to Saudi Arabia border. And this is what we call the benchmark, okay? And that one, we can proceed with it, but unfortunately, we are prevented of getting the instrument because it's gamma, it has radioactivity in it, and radioactivity now is prohibited in Iraq, and I don't know. So this package of, I have to conclude, this package of technology has been applied to 10 hectares of salt-affected soil in Iraq. Results of 5 years have proved the successful and simple application of this method. It is excellent utilization of such wasteland from socio-economically point of view as well as environment. All requirements of this package of technology are locally available. They are either industrial byproduct or farm waste and crop residue. So my friend, this is what we got, like success story reported by International Atomic Energy Agency, and it has been distributed to all member states. Okay, and this is the document we have written, myself and Dr. Sadiq and Dr. Ali Abbas, my colleagues, with the staff of United Atomic Energy Agency about the technology and about the other challenges of salt-affected soil. So thank you, and I hope that I cover most of the area, even though I don't like lecturing, I like the way to present it in a discussion way, but it goes like this, and I hope I did a good job. Thank you.
Thank you for you. Thank you, Dr. Ibrahim, for your very nice presentation. شكرا جزيلا لك. فعلا امتعتنا اليوم بهذه المحاضرة الجميلة اللي طلابنا وأساتذتنا بحاجة إليها. شكرا جزيلا. تفضل دكتور عبد الغفور.
شكرا جزيلا. لحضرة الخبير الدكتور إبراهيم البكري على المحاضرة العلمية القيمة التي ألقاها. الآن نفسح المجال أمام السادة الحضور في حالة وجود أسئلة موجهة إلى كل من الدكتور أندرسون والدكتور إبراهيم. تفضل بطرحها.
نعم، بس تنويه بسيط اخوان رجاء لرابط التسجيل، اللينك التسجيل لغرض الحصول على شهادة المحاضرة موجود على المحادثة على الشات، فرجاء اللي ما هذا يدخل ويسجل. تفضلوا إذا اكو أي سؤال. هذا سؤال دكتور صلاح، هذا سؤال دكتور أندرسون. دكتور أندرسون.
Yes, we are here. Thank you.
Yes, we are here.
This question: how can sustainable application in agriculture processes and land management affected on environment and human health, especially in Iraq?
How could you do techniques to help Iraq to improve the environment or something like this?
Yeah, that's an excellent question. I think my office is good. Okay. How these things we are utilizing here, obviously, I think different plant species. I'm not always familiar with all the ones, but perhaps mixtures of some species that can handle the obviously saline conditions, perhaps challenges with that, as well as the obviously lower in terms of consumption of water. But I think a mixture, again, my understanding is one of the things about the agroforestry type systems is if you can use plants that sort of a combination of plants for different kinds of agricultural use, and I think probably the people are already using these, but basically it helps to, if you can grow different tree species and also other vegetable or other plants, you can help mitigate the severe environment changes that are happening to be able to handle that. But obviously studies have to be done to, one, evaluate, do these combination of plants work together well, obviously meeting the production needs, but they're quite distinct plant species that we have here that are adapted to our native areas, but some native plants in combinations, and some other international areas, sometimes people have gone, I don't think you've in Iraq have done this, but other areas have tried to remove native species and then try to grow kind of some agricultural crop, but then it changes the environment in negative ways, and so sometimes a mixture of keeping some, native species and mixture of some of the agricultural crops can provide some benefits. So I'm sorry, a little bit, since I'm not as familiar with growing certain species in the Middle East, maybe have less background in that. But anyway, an excellent question, and I think a combination of plants growing together can really help.
Thank you. Thank you very much. دكتور إبراهيم.
Yes.
يعني اكو سؤال بالعربي مكتوب يقول احد السلايدات اللي حضرتك عرضتها بها مزروع القطن.
Yes.
يسأل ايش قد يعني نسبة الملوحة او الايسي الموجود في هذه التربة.
He asking Dr. Ibrahim.
ايش قد شنو؟
الايسي ملوحة.
You see, EC always less than 10 decisiemens per meter. I don't have the exact number, but it's less than 10 decisiemens per meter. And you see, it's really surprised all of us that the cotton stay in the same area, in the same field for 3 continuous years, and it's like small shrubs. And when it comes to the flowering time, it's just like white plant. You see, white, all of it white. You see, so it's just beautiful. Okay, really. And we don't know. We just grow it. You see, because we start to grow any kind of salt tolerant crop or kind of salt tolerant crop, and that one, the cotton, helped a lot. Okay.
Okay, thank you, دكتور إبراهيم.
Most welcome.
ما أعرف إذا أكو أي سؤال إخوان الحضور، the audience, any question؟ دكتور نور الدين، أحد؟ any question؟
Too bad not to have a question. You see, you have to ask to discuss.
Is it okay to bring a question to Dr. Ibrahim? Is that okay?
Yeah.
I'm curious. You obviously have sources of gypsum, right?
دكتور إبراهيم، دكتور أندرسون دا يسألك.
You have good, excellent source.
Yes.
Is it too expensive to, or is it work to be able to use gypsum for some of your sodium-affected soils?
Yeah, Dr. Anderson, we have huge amount of gypsum as a byproduct of phosphorus industry in the western part of the country. And there is a train. The train take sulfur, elemental sulfur, from northern part of Iraq and take it to there and return back empty. So instead of getting the train empty, fill it with gypsum and distribute it to the farmers down in the south, in order to create wells. And we found it's really work beautiful for us, you see, because it changed the whole story. You see, it reduces sodium sulfur ratio, it improves the soil condition really well. So a lot of things, and I have several papers published about the effect of phosphogypsum.
Oh, excellent. That's a great strategy to try to use a resource that you have and be able to use it in, obviously the cost is,
yes,
but being able to look at that with a different approach. Excellent. Thank you very much for the response. Thanks.
Yeah.
Thank you.
Thank you.
Any question؟ أي سؤال آخر؟
Well, Dr. Hassan, if you excuse me, I have only one comment.
Okay.
Well, both lecturers were, or scientists, Dr. Anderson and Dr. Ibrahim, were very clear, and the lectures were very nice and very clear too. So there is no question about it. Yeah, you know, Dr. Ibrahim explained everything. So what we can ask?
Very nice. Well,
thank you so much.
Very nice compliment.
We need to discuss.
Yeah, but I am very happy about it. You know, you explain everything, both of you. Well, God bless you both.
You are always in there, Doctor.
Thanks a lot.
You are always in there. You are an excellent scientist. I know.
Thank you. Thank you very much, Dr. Anderson. Thank you very much for your accepting our invitation. Thank you. Thank you, Dr. Ibrahim.
Most welcome, my friend.
Very kind opportunity.
شكرا جزيلا. نحن إذا ماكو أي سؤال ننهي الميتينج. If there is any question. Thank you. دكتور صلاح، عندك شيء أنت؟
لا، أنا ما عندي أي شيء. أنا أشكرك دكتور عزيزي، ممنون من عندك.
نحن شكرنا الدكتور أندرسون، إن شاء الله نلتقي في ندوات لاحقة أكيد يعني.
إن شاء الله أكيد.
راح نتكلم به هو دكتور إبراهيم.
السادة الحضور شكرا جزيلا على حضوركم. إن شاء الله نلتقي معكم في ندوات وورش عمل أخرى. نستودعكم الله وتصبحون على خير.
شكرا
بارك
جزيلا.
الله بجهودكم دكتور عبد الغفور، دكتور حسن، عاشت ايديكم.
شكرا.
وشكرا دكتور صلاح.
نورتنا دكتور نور.
الله يحفظكم.
شكرا دكتور ابراهيم، شكرا دكتور صلاح، شكرا دكتور اندرسون.
Nice meeting you and thank you so much. It was a wonderful opportunity.
نورتنا دكتور ابراهيم، نورتنا.
ممنون حبيبي، اهلا وسهلا، انتم النور، بارك الله فيكم، تسلمون وهاي
for presenting today, and hopefully that we
صحة وسلامة صحة وسلامة
هذا البلد يعني حلو انه في هذا الزمن. ممنون تسلمون.
شكرا للجميع. شكرا نورتونا بحضور.
Dr. Anderson, did you hear me? Do you hear?
Yes, yes, we can hear.
I am now from neighboring state. I graduated from Iowa State back in 1989. So neighboring state, close.
Oh yeah, just a neighbor state just to the north of us. Very similar. So that first study we actually did in southwestern Iowa. So very similar soil to northern Missouri.
Very good agricultural school over there. Thank you.
Yeah, very nice. Nice meeting you. Very nice.
على الندوة ونجاحها دكتور حسن ودكتور عبد الغفور. شكرا دكتور حسن، دكتور عبد الغفور على الإدارة الناجحة للندوة.
شكرا جزيلا لك دكتور جواد. شكرا ممنون. شكرا مرة أخرى الدكتور أندرسون ودكتور إبراهيم. شكرا إلى اللقاء.
شكرا جزيلا دكتور جواد.
شكرا بارك الله فيكم.
الله يبارك فيك.